Okay, welcome back. We're going to cover another example problem right now. Just go to APMonitor.com/DO for dynamic optimization, and then scroll down on the right down to estimator tuning. Okay, so what we're going to be discussing here is after we have an application developed, there might be certain parameters that we can adjust to improve the estimator performance, estimating states or parameters for our system. And so these are some common parameters for example, for moving horizon estimation. At an application level, we have a few diagnostic level that controls how much information is returned. Default is 0 for that. So not a lot of information by default, but you can turn that up and get more and more information from your application as it runs. EV type, that's the estimated variable type. It's going to be 1 for an L1 norm and 2 for a squared error objective. A little bit more information on that. If you just go back to estimator objectives, you can find the squared error objective and an L1 norm objective as well. Let me just go back here. Okay, so manipulated variable tuning. There's cost. If you set that to a positive value, you're going to minimize the manipulated variable. Or if it's a negative value, it's going to maximize the manipulated variable value. Most times that's equal to 0, but it could be equal to positive. Let's say it's a fuel or something else that you're trying to minimize, or a parameter that you're trying to minimize to get a better fit. Okay, decost is the penalty for MV movement. Okay, so this is decost, and what that does is if we have an initial value for our parameter, if the optimizer is going to move it, it's going to pay a little bit of a penalty. So it's going to discourage the movement of that parameter. Okay, so the higher you set that, the less it's going to move. Here we have Dmax. That's the delta maximum that the MV can move each cycle. Okay, we also have feedback status. This is going to be equal to 1 if it's measured and 0 if it's not measured. Okay, lower bound. That's just going to be a lower bound. It's going to enforce that at the solver level. MV type, if you set that equal to 0, it's going to be a 0 order hold, and if it's 1, it's going to be a linear interpolation or a first order hold. Okay, status is equal to 1 when it's on and 0 when it's off, and then of course you have an upper bound along with the lower bound. Okay, some of the controlled variable tuning. Now for moving horizon estimation or estimation, you have basically it's just whether that is the feedback status is on or off. So if it's on, then it means it's measured. 0, it's off. You could also try to minimize or maximize that variable prediction as well. This is another important one, the measured gap or MES gap. That's a measurement gap for the estimator deadband. So if my around each measurement I have a deadband, as long as my model prediction is within that deadband, it's not going to try to adjust the parameters for my estimator. Okay, so you can set options within your script with this APM option command. Just make sure the first argument is your server name, second one is your application name, and then this would be like, for example, a parameter. I'm going to adjust the lower bound of that parameter and just set it to a value of 0. This is one way I can change it within a MATLAB or Python script. Also here is my controlled variable, and here I have a measured, that should be gap. Okay, let me change that, not gas. That's equal to 1. Okay, and then I mode is equal to 8. Okay, so what I'm going to do is now go ahead and change, go ahead and read through this problem. I have an estimator to predict unknown parameters, so the simple model is able to predict the response of a more complex process. Okay, it happens all the time. We make simplifying assumptions for our models, and we want to tune the estimator to achieve either tracking or predictive performance. So tracking performance is that our model values align very well with our measured values, versus predictive performance is something that's just a little bit different. We have parameter values that are going to predict well into the future and have a good model performance into the future. So the parameter values may not vary as much to, let's say, meet noise or other things to track the process really well, but we're going to be able to predict with maybe average values of those parameters over a longer time. Okay, so let me just go into MATLAB first of all. I just wanted to show what we're going to be doing for this. We're going to design an estimator, and we're going to use either a first, second, or 10th order system. Okay, so we want to predict the k and the tau value of a first order model. So that's going to be our model or estimator. And then our actual process that we're going to be trying to predict is going to be a first order, second order, or a 10th order process. So if it's a first order process, if the process is first order, then our first order model is going to do a very good job of approximating that. As soon as we get to a second order process and try to predict that with a first order model, then it's not going to do as well. And then with the 10th order as well, we're going to try to use a first order model to predict the dynamic response of that 10th order process, and there's going to be some process model mismatch. Okay, so that's described right here. And so it's never going to exactly match, but what we're going to try to do is use an estimator to estimate the k and the tau values. And so we want to try to tune this for good tracking or predictive performance. Okay, okay, and then there's going to be a video down here just explaining these. So let's go ahead and just, if you haven't done so already, go ahead and just download these files. Okay, so that's going to be these estimator tuning source files. And the first thing that you need to do is just extract those. Okay, so let me go ahead and just click it, extract all. And okay, so I have my folder with my MATLAB and my Python script. Here's my model right here. So my initial value for my k is equal to 1 and tau is equal to 5. And then I have these two equations. Y is my measurement and x is just a state value. Okay, so just one equation, linear first order system. And then I apply my gain right here for my output. Okay, and then I also have my process model as well. Now this one is going to be a gain of 2 and a time constant of 5. Okay, so I'd have the wrong gain and time constant in my model, and then I can change my process order. I can change it to second order or a 10th order right here, and it will automatically implement that with 2 or 10 state variables right there, and then just divide up the tau into into equal segments, and simulate 10 first order linear equations, and then just my output here where I apply my gain. Okay, so I'm going to set this back to 1. Okay, let's just do this one first, and then I'm going to open up my, let me go ahead and just open up this estimator in MATLAB. Okay, so I'm going to run for a total of 100 cycles, and I have a noise level of 0.5. I can use different servers here. I'm going to use the byu.apmonitor.com. Here's my process simulator that I'm going to load. Okay, so I've given that application 1 name, and then here's my estimator. I've given that application A2 that name, and so I give some tuning here. Okay, there's a lot of tuning parameters. Let me just step through those briefly, just how I set up this estimator. So first I cleared any prior application that was there, load my model, load my data file. Okay, set it to, this is iMode 5, which is this dynamic estimation mode. I can turn up the diagnostic level if I want to get more information. I set my solver equal to IPOpt, which is 3. And then I also set my web plot frequency, so it's going to update my plots every second for me. Okay, and then I have my time constant, my gain as parameters I'm going to be estimating. I'll turn those status values on. And this one, the status value is going to be off, but F status or feedback status is going to be on. And then this is just going to be a state variable. This is the one that's going to be measured, my output Y. Okay, and then I set my status for U to 0, but then I turn on my status for K and tau. Okay, feedback status is on for U, and then for K and tau it's off. I'm not measuring those. but I am measuring the y value. Okay, and then I've set up some Dmax values. Okay, that's the maximum movement per cycle. Let me just open those up originally. So I'll open those up to 10 and 10. So just let it vary almost as much as it wants each cycle. But then I also have a decost. Okay, so that's a penalty on the movement of the parameter. Okay, and that's as the k value moves, that's going to add a penalty to the objective function to weight that. If I put that at a higher value like 100, it's going to move less. Okay, and then also I set my measurement gap equal to 0.5. I should have just set that equal to the this random fluctuation to try to reject the noise. Okay, and then I've just set this up. This is U values that are just going to change every 10th cycle. Okay, it's going to change by a random amount, between -5 and 5 every 10 cycles. So I'm just going to have some random steps that occur within my model input. And then here are the cycles right here. Now, it really isn't that long, but I just go for 1 to 100 cycles. Defined cycles as 100 earlier. This is my process simulator. What I do is I just input my measured value, my U measured value. That's the input to my model that I just defined up above in that other loop. I solve my simulator and then just extract my output Y measured. Now I'm also adding on this this noise right here, just a little bit of noise just to corrupt the measurement. Okay, and the two things that come into the estimator are the U and the Y value. I'm going to solve that, display the output, and then I have my Y, K, and tau that are estimated. And just on the first cycle, I'll open up a web viewer. So let's go ahead and just run this. Okay, so I'll go ahead and change folder here. Okay, and the first thing that it should do is just go ahead and pop up a web viewer when it runs. Okay, so there's the web viewer, and what I want to do is just go ahead and just start tracking Y. Okay, so it's going to update every second, and then as that changes, so you can see that it didn't have to adjust the parameters because it's within that dead band. Okay, but now it may have to start adjusting some of these parameters. It's tracking very well. Let me just go ahead and select this. Okay, and that should go full screen for me. Okay, if I hit escape, so you can see the blue line, my model prediction, it's staying as best it can within that dead band. Okay, right within this measurement dead band. As the measurements come, it's trying to predict. Now again, this is a linear first order model for both my process and my simulator value. Okay, so it's just barely staying within that dead band right around the measured values. Let's take a look at how the K and the tau values are. If you get this orange screen, it just means it was trying to write the plot file at the same time it was trying to load it. If you just select it again, it'll bring that up again. Okay, so here's my tau value. The correct value was 5, and the K value, correct value was 2. Okay, so it does a very good job of estimating those K and tau values. Okay, so you can just evaluate the performance. This one, it does settle out to a value of 2, and then tau. So this is the easiest case. Okay, so a value of 5 and then 2. So excellent predictive performance. So as we talk about tracking performance, it does a very good job tracking. Okay, it does a very good job tracking, and then also it does a very good job predicting these parameter values as well. Okay, so there won't necessarily be equal to 2 and 5 for the higher order case. We just want to see if we can come up with something in terms of an estimator that's going to work well for tracking but also predictive performance. So I'm just going to go ahead and hit Control C here and break that cycle. It's going to go up to 100 cycles for you. Okay, so I'm going to change my process model now. Open that up and just change it to a second order process instead. and go ahead and close it, and then let's just go ahead and run this estimator tuning again, and so it's going to just open up that web viewer. The performance isn't going to be as good, but let's just see if we can tune it so that we get acceptable performance. So here's my Y value. Okay, and then the steps are going to start, and then we'll see a little bit of deviation. Right now there's not a lot of information to estimate the tau and the k values, okay, because there's not really a change that's taken place in my process. You can see a lot of variation in the k and the tau value. So we need a good step response in our model. Okay, so we've got one right there. You can see it start to go out of that dead band just a little bit right here. On the first order model it did just a little bit better. We're going to start to see some deviation because this is a second order system and we're using a first order model to approximate it. Okay, and okay, so we'll let it go for just a little bit, and let's go check out our k and our tau values. Okay, so I'm going to go check out the see how the k is doing. It's coming up with a consistent and steady result. Okay, so about 2.8, it's dropping a little bit here, and let's check out our tau values as well. Okay, so tau went to a max of 10 and is currently dropping to about 8. Now if these parameter values are changing a lot from cycle to cycle and we're passing these off to a controller, then the control moves are going to fluctuate quite a bit as well, even though the target may be the same. So we want to make sure for our control performance that we get consistent values going forward in time that are going to predict well. Okay, so here we can see quite a bit of movement on the tau value. So let's just do a couple things with the tuning to try to dampen out some of those fluctuations and get maybe a more consistent prediction going forward. Okay, let's just look at the k value one more time. Okay, so k value is leveled out. This looks pretty good on the gain, and the time constant is still dropping just a little bit. Okay, so I'm going to go ahead and close this, and then I'll stop this one. Okay, with the Control C again. Okay, and then come back into my estimator tuning, and some of the things I might start changing then are this Dmax. So if I set that to a lower value, so let's say 0.5 or 0.1, then it's going to change less each cycle. Now those may not be correct values going forward, but at least they'll be more consistent. It won't fluctuate as much. The other thing I can do is I can penalize movement of those parameters, okay, with DCOS. I can also adjust my measurement gap. So if I increase it, I might say, well, I really only want to match large deviations of my model, but just for random fluctuations, I'm not going to try to correct my model for just these random fluctuations. Okay, so let me go back in and just start this one again and see if we get any better performance, more consistent values of our k and our tau values. Okay, so I'm going to open up the y value. This is our measurement, and I'm predicting with the blue. Okay, you can see that it starts, this is my horizon right here. I can also increase or decrease this, but I go back, I think it's about 20 or about 40 steps. Each one's about 0.5 seconds, and going back for 40 time steps. So I can also adjust that. That's part of the estimator tuning. So I have a little bit bigger dead band here. Okay, so it's not going to try to adjust it unless it's outside that dead band. So here it's working on the parameter values. I may have had a delta move, change on my k and my tau values. So let's just look at that. Okay, so I have, it's not fluctuating quite as much. You can see it's just going to kind of level off here at, that looks like 2.5. And let's just look at my tau values as well. Okay, again, you didn't have the big fluctuations at the beginning. I had a larger D cost value, and then it has leveled off here right around 10. So let's just, so I think overall the gain is probably a little bit more consistent. Actually, that is going down. Okay, so these sawtooth functions, if you see sawtooth functions like this, it may mean that your Dmax is over constrained, that the optimizer was trying to drive it up, and then it got to a certain point, now it's trying to drive it down, but its rate of change limited, and so we're going to continue to possibly see these kind of sawtoothing effect if your Dmax is too constraining. And that looks like what's happening, maybe what's happening here with this. So I may need to relax those Dmax constraints. Okay, so let me go ahead and stop it now. And so this was not very good performance. Okay, so you can actually over constrain these and actually get worse performance. Okay, so hit Control C to stop it, and then I'm just going to open these back up. I'll just try to use the D cost, okay, along with my increased measurement gap. Okay, and then it's going to go ahead and start again. Okay, and here's the new interface. Okay, so tuning is sometimes a tedious process, just because you could use the for these tuning values. A theoretical optimum is to use the inverse of the covariance matrix with a squared error objective, and that's should be the optimal tuning values. A lot of times we don't have the inverse of we don't have the measurement noise covariance. This can be hard to get, especially for a lot of measurements. Okay, and it looks like that one is interesting. It looks like it's getting just a completely different value here. Let's just check our U values. Okay, so that went up to 3.5, and if I look at my tau value and my K value, okay, so you know what, this is not giving me much better performance than I had before. So it looks like something happened with my simulator. Actually, I think just my process model is not doing very well here. Okay, so again, I'll just need to go back and adjust some of these tuning parameters, see if I can get good tracking performance, but also good predictive performance of these. Okay, so just if you can come to these K and tau values, just get a feel for how these predictive values are changing, and how to adjust some of these tuning values to get the best performance of your estimators. Okay, so there's also a Python script as well. If you'd like to use the Python script, it should be exactly the same as the other one, and then if you run it, don't forget to just change this process.apm file. Both of them will use that, and just change the order of that to get your different performance. And this again will open up the same web viewer for you, and then you can just go to dashboard and look at the same plot that you were with the MATLAB script. Okay, so there they are. There's the this is the example with estimator tuning. And come back here. I'll go ahead and kill this process. Okay, so I'm going to come back to the web page. So just to summarize, we want to design an estimator to predict unknown parameters. So the simple model is able to predict the response of a more complex process, And we want to tune this estimator to achieve either tracking or predictive performance. And in this case, estimated time about 2 hours.